a quick video on the assumptions and conditions for the regression, slope, t-test, and interval. So the last set of notes that you looked at, we were looking at comparing anxiety levels to math test scores, and all we did was give you a computer printout, which was just showing you all of the statistics that they gather to do the linear regression and then to go through and do the test. So what we're going to do today is talk about, was it even appropriate for us to have done that? Maybe the data that we get doesn't meet certain assumptions and conditions necessary to complete a regression slope t-test or even the t-interval. So there is a new set of assumption conditions. You'll see some repeats, but these are going to be specific to linear regression and using them to do a slope t-test or interval. So because of that, your book was kind of clever and came up with this mnemonic for the fact that we're doing linear regression. So they put it in the order of liner. It's not really linear because there's an A missing, but it spells liner, and it might help you to remember that there are 5 assumptions and 5 conditions to check. So we'll go through each one of them generically to describe what they are, and then we'll do an example together. So the first one is L for linear. This is actually something we definitely checked back in chapter 3. When we're looking at data, it would be inappropriate to do linear regression if the data is curved in any way. We're actually going to talk about nonlinear data in the next section. So for right now, it must be fairly straight data. We call it straight enough. Needs to be straight enough. But the best way to check that is to look for no pattern in the residual plot. So if you recall, a residual plot is a graph of each of the individual x values and their associated residuals, which is how far away each point is from the line. And the residual plot shouldn't have any curve or anything to indicate that the points were curving around the line. So we don't want to see that. Let's go ahead and do that example down below. So I have actually 3 graphs for you. This is just the regular scatter plot of the anxiety levels and the math test scores. And you can see that negative trend that we saw last time. But we also, I can see there was quite a bit of scatter. There was some people that had, some low anxiety and still got low math scores, and some people had fairly high anxiety and still got good math scores. So there was quite a bit of scatter. We also remember we had an R squared of 27.6%, so that kind of explains this graph a little bit. The next is your residual plot, and you'll know that because it's still a scatter plot, but it says residuals on the y-axis. And then finally, this is a histogram, or it might be an NPP, but it's some sort of one variable graph of your residuals. So not to confuse it with a residual plot, this one is in order. The residuals are in order from the lowest anxiety level to the highest anxiety level. These are just like the smallest residual to the highest. It's irrelevant of what the anxiety level is. And we want to see, we're going to be looking at this later on in our assumption and conditions. So let's start. I usually number them just to make sure I don't forget them. I know I have 5 of them. So linear is the first assumption. And you can look at the scatter plot, but the better thing is the residual plot, and we see no pattern. So yes, we can assume linear data because the residual plot has no pattern. So it's kind of annoying. You do have to write like a little sentence for almost all of these. You have to write a little sentence to indicate that you've looked at the appropriate graph and that you understand that that's an appropriate condition to check. All right, next, I for, independence. We've had this one all along. This one is that the individuals are independent from each other. We actually have 2 things, as always, with independence. We have the 10% condition, but we also have random to check, but they decided to put that down here to finish the cute little liner thing. So we can jump back down to the bottom. And the data collection we actually talked about last time, it said that there were 24 pieces of data, and that's definitely less than 10% of all students, I guess we can say. Less than 10% of students that are in a math class, maybe. Check that off. All right, the third one is a normality check. We have quantitative data, so we have to make sure that we have data that is reasonable to assume is normal. But what we'll be looking at for normal, usually we look at our data to see if it's normal, but we've got X and Y data. So the correct thing to check for normality with these slope tests and intervals is to check a one variable graph of the residuals and look for nearly normal. All right, so just like with a scatter plot, you know, we can say straight enough. With one variable graphs, we sometimes ask you to see if they're close to being a normal model. So what you're looking for, and this is the graph we're going to look at for normality, is we're looking for, you know, really just one main peak and generally not any extreme skewness or outliers. I think our data looks really good, so we can go ahead and assume normality is met. So you state the assumption, and then you say the histogram of the residuals is approximately unimodal and symmetric. So that one's looking good too. All right, out of all of them, this one is the newest and strangest one. It is E for equal spread, or sometimes they say equal standard deviation, but E for equal. This is where we want to not have some sort of an unequal variation as we go across the X values from left to right. We don't want it to be that the graph is showing really small residuals in some places and then bigger residuals in others. You can see that sometimes in a scatter plot, but it's better to look at a residual plot, and you want to kind of look for a nice like tube of points or rectangle shape of points. You don't want to have like a triangle shape, meaning again that you've got close residuals and then they like spread out or fan out later on, or the other way around. You don't want it to be far apart at the beginning and then narrow as you go in. Our residual plot's looking good, but let me just explain that up top. You want to look at the residual plot for even spread across the X values. All right, I think ours looks pretty good. I'll show you some examples in class where they won't look so good. They'll have this like triangle-like shape. So you call it equal spread. And you'll just say the residual plot shows fairly even spread across the anxiety levels. All right, last one. So there's 5 of these. Is R for random. So we usually do that one first, and they just put it at the end to be in the liner kind of thing. So it should be a random sample from the population. That was actually not stated. We need to think back to our information from last class, where they talked about where they got this data from. I think it was just like a class of students, and they just checked their anxiety level and then their math test scores. So we need to just say random, not stated. I guess we can proceed with caution. Okay, so we've said before that oftentimes you'll get questions that just ask you about assumptions and conditions. So it's important that you understand all of the things that you're supposed to assume to be able to do the problem, and how to actually check and what condition will give you a good estimate of whether that assumption has been met. If you flip over to the back, I photocopied an example from your book. I'm sorry, it's kind of tiny. Here's your computer printout, but I don't actually want you to do the test or interval. I just want you to look at these graphs and do exactly like we did on the front, write out the assumptions and conditions. I think based on the notes on the front, you should be able to do that on your own and come back to class with that done. Thanks so much. Bye-bye.